Hi, honors friends. Today we're going to look at section 6.8. This is the last section in chapter 6, and it involves the counting principle. You'll need your books open to page 327, and you can follow along. A couple of these examples that I have on your note sheet actually are in the textbook. And you can see on page 327, example number 1 involves a tree diagram. The definition for tree diagram is in your textbook also, and you're able to copy that definition, and I won't be writing it down on the notes. If you look at the tree diagram in example 1 about these kids' choices for glasses, you might remember making a tree diagram in 5th or 6th grade. And that's a great way to identify all of your possible options until your choices get really large. And so fortunately, there's a mathematical way to identify how many choices you have, not without having to make a tree diagram. And that is called the counting principle, which is on the top of page 328. I think they call it the multiplication principle. But basically, the counting principle says, however many options you have for each of your choices. So let's take an example. In the example number 1, the glasses choices were plastic or metal, so there were 2 options. And then they had 4 different options of shape: rectangular, oval, cat's eye, or round. So 2 options. This was metal or plastic. And these were one of 4 shapes. The counting principle says multiply these 2 guys together, and that's how many possibilities there are of combinations. So you can see the 8 combinations listed in the tree diagram, and then you can see it calculated without a tree diagram by simply multiplying how many choices you have together. So let's look at this birthday cake example. This is pretty straightforward. It can either be a round or a rectangular cake. So there's the shape. That's our first choice. Vanilla, chocolate, and lemon are the choices for cake flavor. So cake flavor is the second thing we're picking. Oh, and that's it. I didn't even put any frosting on here yet. So it says use a tree diagram to find out how many birthday cakes there are. So we could have a round vanilla cake, a round chocolate cake, a round lemon cake. Or we could have a rectangular vanilla, rectangular chocolate, rectangular lemon. This is my idea of a tree diagram. It's really just a list, but that's okay too. And it looks like we have 6 possibilities if I haven't left any out. If we use the multiplication principle, the counting principle, how many choices for shapes did we have? Just 2, round or rectangular. How many choices for cake flavor did we have? 3. 2 times 3 is 6. Now I don't know about you, but I prefer this short little mathematical way to calculate my number of options rather than making a list or a tree diagram. Suppose you also have a choice, here are my frostings, of buttercream, cream cheese, or whipped frostings for your cakes. So we had 2 choices for shapes, 3 choices for cake flavor, and now we have 1, 2, 3 frosting choices. Now, if we had to draw a tree diagram, it would get more cumbersome. So we're going to use the counting principle, and we're just going to say, well, 2 times 3 is 6, times 3 is 18 total possibilities. And we certainly could make a tree diagram if we wanted to, but we're going to solve most of our stuff using the counting principle. All right, sandwich shop. Let's see how many possibilities we have. Makes egg salad, tuna salad, chicken salad, turkey, or roast beef. So that's the filling. Let's see, 1, 2, 3, 4, filling or inside of sandwiches. There's 5 choices, and there's wheat, rye, or white bread. So if we just used those 2 criteria, we've got 15 possible combinations with just those 2. Now, here's my challenge. Jonathan, maybe this will be for you. I want you to walk into Subway and see if you can use the counting principle to figure out how many choices we really have. Ha ha. I'm not sure we could do it. When you think about not only the bread type and the inside, but when you think about mayo, mayonnaise, dry, you think about toasted or not toasted, tomatoes, no tomatoes, lettuce, no lettuce, what kinds of cheese. Oh, Lordy, the endless amount of possibilities. But we could actually figure out, we could probably get pretty close. All right, let's keep going. You roll a red and a blue dice. Now let's assume that this is a 6-sided normal dice that's got the numbers or the dots 1 through 6 on them. Use the counting principle to find out the number of different outcomes that are possible. Now if I asked you to list these, you might say, okay, I can get a 1 on the first roll and a 1 on the second roll. I can get a 1 on the first roll, a 2 on the second roll, a 1, a 3, a 1, a 4, a 1, a 5, a 1, and a 6. This is just the first set of possibilities if you roll a 1. So we're going to have a pretty long list if we list them. But using the counting principles, we ask ourselves, how many possible combinations do we have on the first roll? We have 6 things that can happen. It's like 6 choices of bread. How many things can happen on the second roll? 6. Multiply them together and you get 36 possibilities. This is 6 of them. You would have 5 more lists that look just like this with the numbers 2, 3, 4, 5, and 6 to get your 36 possible combinations. Now let's talk about probability from the last section. So out of these 36 combos, what's the probability that your pair is going to look like this? 6, 6. Well, remembering that probability is favorable outcomes over total possibilities, total outcomes, we'll apply that and we'll say, well, the total possible outcomes is 36. I just calculated that right there. How many favorable outcomes are there? How many ways are there to roll a 6 on the first dice and a 6 on the second? Just 1. So the probability that you're going to roll 2 6s is 1 out of 36. So we used the counting principle for the denominator, and then we used our favorable outcome and total outcome formula from the probability to actually come up with the fraction for the probability. All right, let's look at another one. A combination lock, like you have maybe on your school locker, has 40 numbers on its dial. To open the lock, you go to the right to the first number, left to the second number, and right to the third number. You randomly choose 3 numbers on the lock. What's the probability that you actually have chosen the combination? Well, first thing we need to do is figure out how many total combinations are there possible. So you have 3 numbers on your dial. You ask yourself, how many choices do I have for position number 1? 40. How many choices do I have for number 2? They didn't say we can't use the same number more than once, so we have 40 selections for number 2 and 40 selections for number 3. So if we have a calculator handy or a good mind as a calculator, we can multiply 40 times 40 times 40 and we get 64,000 combos for your locker. Now we're asked to find the probability that you can guess the combination. So favorable, which is your combination, over total outcomes. We know the total outcomes is this 64,000. There it is. How many favorable outcomes are there? I'm hoping you're thinking there is just one. Your combination is unique. There is just one. So you do not have a very good chance of guessing somebody's combination. And that's the way it ought to be. Okay, I think we just did that. That was 1 out of 64,000. All right, and one more of these, I think, before I turn you loose on your own. Your school is issuing a 5-digit ID number to each student. The first digit must not be 0. What's the probability that your ID number is exactly this? So, let's figure out how many possibilities there are. Here's your first digit, second, third, fourth. Here's your 5 digits. Now, there are 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10 digits. But this first digit cannot be 0. So that means we only have 9 possibilities for this first number. But each of these other numbers has 10 possibilities. It doesn't say that we can't repeat a number. It doesn't say that there's any restriction at all. So if we multiply these together, we get 10 times 10 times 10 times 10 times 9, which is 90,000. And hopefully you could have done that with exponents, powers of 10. 90,000 combos. That becomes the denominator of our favorable outcomes over total outcomes. So the 90,000 is the total possibilities, and there's only one out of those 90,000 that's unique to you. So that's an introduction to the counting principle. It's pretty easy. It's kind of fun. It's a short little section, and you should now be able to do your homework in the book, and I look forward to seeing you when I get back. Bye-bye.